My name's Hailey Brookins, and my project is modeling drought severity with meteorological predictors. Droughts are a natural part of the climate cycle. However, it is becoming increasingly important that we understand their full causes and effects, as climate change is exacerbating drought conditions in several regions of the world. In the United States, for example, the Southwest is at a particularly high risk for droughts. Climate change contributes to drought in several ways. Firstly, warmer temperatures increase the amount of water that evaporates from the soil. Climate change is also altering atmospheric rivers, where water moves through the atmosphere, which alters precipitation patterns. Predicting future precipitation is not an exact science, but climatologists predict that with a warming climate, wet regions will get wetter and dry regions will get drier. In other words, as the climate gets warmer, droughts in dry regions will become even more severe. This increase in drought severity is important because droughts have a range of detrimental effects, including losses in agriculture, water supply, energy production, public health, wildlife, and increased wildfire severity. As the climate warms and droughts become more common, these effects will become even more severe. Droughts, unlike other natural disasters, can be hard to identify. Droughts are defined as periods of drier than normal conditions for a given area. In some parts of the world, 4 inches of rain per year is normal. In others, you can expect 50 inches of rain. So droughts look very different in different regions. In other words, there isn't one amount of precipitation that indicates a drought in any region of the world. This subjectivity can make droughts hard to identify and quantify. The authors of the U.S. Drought Monitor are addressing this challenge by comparing current precipitation levels to climatological averages in regions across the United States. The U.S. Drought Monitor is a map that comes out every week that classifies the areas of the U.S. that are experiencing drought. It is not a forecast, but rather a measurement of the drought conditions of the past week. There are 5 categories, D0 to D4, that increase in severity. The D0 category indicates regions that are abnormally dry. This category is often used for areas that are going into or coming out of a more severe drought and indicates short-term dryness. D1 indicates moderate drought, during which there will be some damage to crops and pastures, streams, and reservoirs or wells are low, and people will be asked to voluntarily use less water. D2 droughts are severe and mean that water shortages are common and water restrictions will be imposed. The D3 category indicates extreme drought conditions, during which there will be severe crop and pasture losses and widespread water shortages. The last category, D4, is exceptional drought, which indicates widespread crop and pasture loss and emergency water shortages. The authors of this map determine the weekly classifications for each region by synthesizing several inputs, including the Palmer Drought Severity Index, the Standardized Precipitation Index, and other climatological inputs, the Keach-Byram Drought Index for fire, satellite-based assessments of vegetation health, and various other indicators of soil moisture, and hydrologic data like Surface Weather Supply Index and snowpack. This map is jointly produced by the National Drought Mitigation Center at the University of Nebraska-Lincoln, the United States Department of Agriculture, and the National Oceanic and Atmospheric Administration. The purpose of this project is to determine whether meteorological conditions impact drought occurrence and severity. This dataset came from Kaggle, an open-source data sharing website. It combines weather data from NASA with the drought severity classification from the U.S. Drought Monitor from D0 to D4. The datasets were combined by county from 2019 to 2020 and include 18 meteorological predictors like precipitation, wind speed, humidity, and temperature. The graph on this screen is a histogram of the raw data of the drought score column, the response variable for these models. As you can see, the data is clustered around integer values, but some entries do include decimals. Because this dataset is a combination of several, there is some discrepancy in how the score column was calculated. Some collectors used integer values, while others included decimals. Because of this discrepancy, 2 models were created that measure the impacts of meteorological data on the drought score, one of which categorizes the drought score into 5 classes by rounding to the nearest integer, and the other of which uses the score column as is, which is a clustered numerical response variable. The first model is an ordinal logistic regression model. Like other regression models, it determines the impact of the explanatory variables on a response variable. Ordinal logistic regression is unique because its response variable is an ordered categorical variable. In other words, the model accounts for the fact that the order of the categories in the response is meaningful. In this case, the drought score goes from least to most severe as the number increases. One important assumption made by ordinal logistic regression models is the parallel slopes assumption. This model assumes that the relationships between all pairs of responses are the same. For example, the relationship between D0 and D3 is the same as the relationship between D1 and D4. This assumption means that the model only produces one set of coefficients rather than several sets that compare each of the response categories to all of the rest. The second model is a Lasso regression model. It also determines the impact of several predictor variables on a response variable, but in this model, the response variable is numerical. Lasso regression models are unique because they use shrinkage to eliminate less relevant parameters. In other words, the model will disregard predictors that aren't significant. Due to severe collinearity between several of the meteorological predictors, these regression models used only precipitation, specific humidity at 2 meters above the canopy, wind speed at 10 meters above the canopy, temperature at 2 meters above the canopy, and surface pressure to predict drought scores. The first model I created was the ordinal logistic regression model, which predicts an ordered factor response variable. This model returns coefficients that are scaled in terms of logs, which are very hard to interpret. So, rather than using coefficients to determine the outcomes of the model, I converted them into odds ratios, which are much simpler to interpret. The resulting odds ratios for this model are shown in the table. For every 1 millimeter per day increase in precipitation, the odds of the drought level going down increase by 3.2%. For every 1 gram per kilogram increase in absolute humidity at 2 meters above the canopy, the odds of the drought level going down increase by 37.4%. For every 1 meter per second increase in wind speed at 10 meters above the canopy, the odds of the drought level going down increase by 6.9%. For every 1 degree Celsius increase in temperature at 2 meters above the canopy level, the odds of the drought level going up increase by 79.2%. And for every 1 kilopascal increase in surface pressure, the odds of the drought level going down increase by 48.3%. The next model I created was a Lasso regression model. As a reminder, unlike ordinal logistic regression, the drought response variable for this model was an unaltered clustered numerical response. Because Lasso regression models use shrinkage, not all the predictors will necessarily be included in the final model. Lasso regression uses a lambda value to determine which predictors are useful and which aren't. The graph on the left shows the coefficient values for each of the predictors at different lambda values. As you can see, as lambda increases, the coefficient values shrink towards 0. The model chooses the best lambda value by calculating which would result in the lowest mean squared error. The lambda value for this model ended up being 0.0003. The coefficient values for each of the predictors with that lambda value are shown in the table. There is a dot on precipitation because this Lasso regression model with the chosen lambda value removed precipitation as a useful predictor. The shrinkage of precipitation is also clear on the graph of the lambda values. Precipitation is the orange line, and it stays near 0 on the entirety of the graph. Humidity, wind speed, temperature, and precipitation predictors were used in the final Lasso regression model. As humidity goes up by 1 gram per kilogram, the drought severity is expected to go down by 0.096. As wind speed goes up by 1 meter per second, the drought severity is expected to go down by 0.027%. As temperature goes up by 1 degree Celsius, the drought severity is expected to increase by 0.107. And as pressure goes up by 1 kilopascal, drought severity is expected to decrease by 0.307. Each model calculated different coefficients for each of the 5 predictors, but the general impact was the same across both for every variable but precipitation. In the ordinal regression model, more precipitation decreased the odds of a more severe drought. Intuitively, this result makes sense. It is expected that less precipitation would increase the odds of a more severe drought. However, the Lasso regression model shrunk precipitation out entirely. According to the National Drought Mitigation Center, predicting drought depends on forecasting two things, precipitation and temperature. So why was precipitation insignificant in the Lasso regression model? The variation in average precipitation between different regions and the unpredictability of changes in precipitation patterns likely explain why precipitation was moved as a predictor. It was hypothesized that there could be a collinearity between humidity and precipitation that was affecting the precipitation result, but no collinearity was found. In a study conducted by the National Oceanic and Atmospheric Administration, researchers found a negative relationship between humidity and drought levels, and several other studies confirmed this conclusion. My results also confirm this relationship, as both models found that lower humidity levels were predictive of more severe drought conditions. The United States Geological Survey found that higher wind speeds are associated with higher rates of evapotranspiration, meaning that high wind speeds cause more water to evaporate from soils, and therefore worsen drought conditions. In fact, almost all published literature has found that stronger winds mean more severe droughts. These models, though, predict that higher wind speeds mean less severe drought conditions, which contrasts more common conclusions about the relationship between wind and drought. Several studies have found that high temperatures are correlated with drier drought conditions, particularly during local growing seasons. Other studies found that some droughts are correlated with lower than average surface temperatures. In both the Ordinal Logistic Regression and Lasso regression models, temperature was highly predictive of worsening drought conditions, adding to the conclusion that drought is worsened by warming temperatures. According to the National Drought Mitigation Center, and this is a direct quote, "The immediate cause of drought is the predominant sinking motion of air, subsidence, that results in compressional warming or high pressure, which inhibits cloud formation and results in lower relative humidity and less precipitation." These models contrast this relationship, as both used a decrease in pressure to predict worsening drought conditions. Several studies have been conducted about the relationship between weather and climate and drought conditions. However, this model uses data from 2019 and 2020 to create predictive models for drought severity specific to the United States. The coefficients of these models confirm the results of several previous studies and add a predictive component to more general correlations. If an accurate model was created that used weather and climate data to predict when droughts would occur and how severe they would be, water and other resource managers could make more informed allocation decisions. Regions that are predicted to have droughts could implement water restrictions earlier to reduce the impacts of drought on food and energy production, public health, and wildlife populations. Both of my models have severe limitations. Neither are in their final stages, so these results are preliminary. A more thorough explanation needs to be conducted of other possible collinearities, including between humidity and pressure, between wind speed and pressure, and between humidity and temperature before these models are complete. These collinearities could explain the unusual results of these models about pressure and wind speed. Variable importance also needs to be analyzed to determine which of these predictors have the greatest impact on drought severity. Future research should look to further explain the complex relationships between these predictors and drought severity. It should also aim to add other variables to these models that would improve their ability to predict drought conditions. Next, future research should work on identifying the true connection between wind speed and drought conditions. Models should be created that are region-specific to determine whether these relationships are specific to certain areas. Lastly, other types of statistical models should be created to determine which are most effective at predicting droughts. This is a list of my references, and here is my contact information. Please feel free to send me an email if you have any questions or if you're curious about how the final models turn out. Thank you.